And still the Navier Stokes equations. So we were discussing the flow, the inviscid flow passed on airfoil. We saw the first case, let me remind you, the first case was steady viscous laminar flow in a horizontal pipe. In that case, steady, so dV dt is 0, and convective acceleration was 0 because all the velocity profiles along the pipe are the same, and we just had the pressure and viscous term. Then the second example we had was flow past an impulsively started plate. Impulsive acceleration, we have the local term, the local acceleration term, the unsteady term is not 0. And so you have there a balance between the convective term and the viscosity term. So it's like a heat equation. And then the third example was boundary layer flow. For boundary layer flow, we have just the viscous term and the convective acceleration. We saw already we can't get an analytical solution for that because we have the convective term, which is nonlinear. Then the fourth example, we have again the convective acceleration, but instead of having viscosity, we have pressure as the driving force because we just assume that it's inviscid. Right? So it's a balance between pressure forces and convective acceleration. Again, we can't find a closed form solution. It would require computational approach. The next case is impulsively started flow of an inviscid fluid in a pipe. We saw the first case. The first case of impulsively started flow was on just a flat plate open to the atmosphere. This is in a pipe. So we will neglect the hydrostatic terms just for simplicity. They're small. And there's in this case we have a balance among the convectively we have let's see, we have it's impulsively started, so we have unsteady terms. And but all of the pressure, let me see if I can start this picture here. All of the, since it's inviscid, okay, the viscosity terms are 0, so no viscous forces. And we don't have to apply the no-slip boundary condition in this case. We're assuming that there is no effect of the boundary on the flow. So we have slip on the boundaries, okay? If we had what was it? The first case we saw, right? We had a parabolic profile, laminar flow inside a pipe. The velocity had to go to 0 at the wall, right? In this case, we have no viscosity. It's idealized case. The velocity doesn't have to go to 0 at the wall. There's no reason for the fluid to slow down, right? So it's completely uniform. But it's impulsively started. So all we have is this effect that this is not 0 because it's impulsively started. There's no viscous forces. So all we have is the pressure. The profiles along here are all the same. So there's no convective acceleration also. The convective acceleration is 0 because the velocity does not vary in the direction of the flow. So we have the pressure term and we have the unsteady term. And that's it. So a balance between local unsteady acceleration effects and pressure differences. And here the velocity is basically just a function of time. The local acceleration basically is not zero because the velocity at any point, the velocity at any point is a function of time. So all of these are variations of the Navier Stokes equation for simplified cases. Let's look at yet another one. Number 6, viscous flow, steady viscous flow past a circular cylinder. Partials with respect to time are equal to 0. There's no local acceleration. And so this flow represents a balance between convective acceleration, pressure gradients, and viscous effects. It's viscous. So now we have pressure, we have viscous effects. The velocity now, let's write it as a vector. I think we chose to use, let's be consistent, capital U for the velocity in general. And on the other side we have the convective term. This nonlinear term here. This represents a balance between convective acceleration pressure gradients and viscous forces. And here's a little cartoon of a particle of fluid going around the streamlines which are drawn there for steady flow. Yes?
Would in viscous flow, the same situation be the same?
No, would be different. In terms of the picture that we're seeing here?
In terms of the picture, like when it's just the back flow, I think maybe be slightly longer.
No, in the case of an viscid flow, you actually can obtain a solution which is symmetric. You don't have this area in the back. There's no reason for the flow to slow down around the cylinder, right? Because it's inviscid. And so the flow slows down around and then accelerates in the back, and basically you have completely symmetric flow. So in the inviscid case, it's the streamlines go around completely like that. Not very pretty, but you get the idea. Okay, let me just say that we have assumed here that this is steady, okay? We've assumed that this case is steady. Now, this steady flow around the cylinder like shown here will only occur for very special combinations of the parameters here, which are the viscosity, the diameter of the cylinder, and the density of the flow, and and the free stream velocity. Let's call it V0, this sort of unperturbed velocity before approaching. And this will this is so for other cases of these parameters, the flow will be unsteady. Most generally, the flow will be unsteady, okay? But we're trying to show some idealized cases of increasing complexity. From 1 to 6, we've seen increasing complexity. Already, we can't obtain a solution, okay? There's no known general solution for this case. Already, again, we have this nonlinear term that messes everything up. Very difficult to deal with that. The final example that I will show you is, or discuss, is unsteady flow past an airfoil. We had the steady case, now the unsteady case. In the unsteady case, well, basically all the effects are considered. We have local acceleration, we have convective acceleration, pressure gradients, the viscous effects, and unsteady terms. All of the terms are included here. And we have the full equation, which is the only one that we can neglect is hydrostatic effects, basically, because the flow, the changes in elevation are quite small. So, but we do have pressure, we have the viscous terms, and we have the unsteady terms, and the convective acceleration. All of these are included in this case. All of these are involved in the balance of forces. Now, in this case, the flow is very complicated. The movie shown there is actually a visualization of the flow around an airfoil at a certain angle of attack such that the flow becomes separated. And you can see that this is unsteady. It's a very complicated flow. There's no solution that we can write for the Navier Stokes equations, and the only approach is computational. And here on the right, there's a calculation using computational fluid dynamics, where each one of those little, white dots represents a particle of fluid that is being tracked by the calculation. Of course, the angle of attack in the picture on the right is much larger than the one in the actual experiment. And indeed, with computational fluid dynamics, one can, with a lot of difficulty, it's not easy even, obtain a solution for the velocity and pressure at every point in space and at every instant in time. So, I was saying that the only general approach is to use computational fluid dynamics, and we will discuss a little bit about that. We'll have an introduction in the future, in a couple of lectures from now. But we have to discuss a couple other concepts around this that we've introduced today, these various types of flow that we've seen. The first concept, if you recall, the first case that we showed, it was titled steady viscous laminar flow in a horizontal pipe. So what does that mean? Just to be sure that we understand that, the difference between laminar and turbulent flow. Let's discuss this for a little bit. This particular case that we started with in this overview represented a balance between the pressure difference, if you recall, along the pipe, and the forces which result from viscosity. And that balance between pressure and viscous forces produced a solution, which we're able to write in closed form, which is a parabolic velocity profile, right? That parabolic velocity profile, in fact, is called, for pipe flow, is called Poiseuille flow. This is the name of a French engineer. Poiseuille flow, parabolic velocity profile. It has a shape like that along the pipe. Okay? So this solution that we obtained of the Navier Stokes equations assumed, of course, steady conditions. And the question that one may ask after the solution is obtained is, how does it correspond to experiments? Experiments of pipe flow have shown that, in fact, this analytical result is quite a good description of what's happening in the pipe, but only if the flow is laminar. Okay? This parabolic velocity profile is shown experimentally to be a good approximation of the flow only for laminar flow. So what does that mean? Laminar flow basically is experientially speaking, from the point of view of the experiments, it means a flow which is basically orderly, smooth, right? Every layer of fluid moves neatly on top of each other. In contrast, turbulent flows are chaotic, unsteady, and unpredictable. This is sort of a qualitative explanation, so we need to have some form of more specific definition for engineering terms. But let's just qualify first laminar and turbulent flow. And fluids maintain, relative positions to each other which are smooth in the laminar case, and in the turbulent case, the flow is chaotic, or it seems to be chaotic from our perspective, and never steady. Now, whether a flow is laminar or turbulent depends on a combination of effects. Basically, it depends on the balance between viscous and inertial forces. The inertial forces are related to the acceleration, and this is expressed by the Reynolds number. Which we define as the density rho times a characteristic velocity v, a characteristic length divided by the viscosity. So why is this the balance between inertial and viscous forces? So inertial forces are characterized by the nonlinear terms. So, for example, a term like rho u du dx. Nonlinear terms. Okay, so if we wanted to sort of write a characteristic sort of term that describes the inertia in the flow, we could use something like a characteristic velocity, v. We have one v here, and then we have another v and a length, right? So v squared divided by length. This would be the inertial, a measure of the inertia of the flow with a characteristic velocity and a characteristic length. So if we were talking about the pipe, the characteristic length could be the diameter. This could be the characteristic length, and the characteristic velocity could be v, the average, right? And that would indicate the quantity, the amount of inertia in the flow. The viscous forces, of course, are exemplified by the term, if we're looking at the 1D case, would be characterized by terms of the form like that. Second derivative of u with respect to x. All the terms of this form, whether it's with v or w or u, or whether it's, all of these terms are characteristic of viscosity. So we can write a sort of characterize the flow by looking at terms of the form mu, and here we have one velocity and two lengths, basically, right? In this type of looking at just the dimensions that are involved there in that term. And so if we want to write a ratio between the two, you will see if I put a ratio between inertial forces, I'm going to have to sort of find a spot to write this. I'm going to just make a little extra spot for myself here and write a ratio between inertia and viscous forces, and it's going to be rho v squared over, let me write it like this, over L, and viscous forces is mu v over L, and you see that I get the Reynolds number, right? So this is what the Reynolds number represents, this ratio between inertial and viscous forces, rho VL over mu. Sorry? Where do, oh, the square here. So the Reynolds number is actually a very important quantity in the flow, and we can use the Reynolds number for different flow situations to actually determine whether a flow is laminar or turbulent. If the flow is dominated by inertia effects, the flow is much more likely to become steady and to become unsteady, I meant to say, and have instabilities and so on, and that would be a turbulent flow. If the flow is dominated by viscous effects, then it's much more likely to be laminar. And so low Reynolds number is associated with laminar flow, and high Reynolds number is associated with turbulent flow. But where the value, where there's sort of a change between one and the other will depend on the geometry of each situation. But it's a very important parameter to classify flows. And to give you an example, in this video we see jets entering a still fluid and for different Reynolds number. Only for the case of the further right, I wish I could have see this again. Let's see. Only for this case in the further right is the flow can it be characterized as turbulent, and you can see in the other cases it's much more orderly, and layers of flow can be seen to very, very neatly fold around, right? And so there is, for this flow and for any other flow, a critical value of Reynolds number below which the flow is going to be laminar and above which the flow is going to be turbulent. This depends on the flow, but for the particular case of the pipe flow, we kind of know approximately that when the Reynolds number is less than about, not exactly, but about 2000, then we'll have a laminar flow. And when the flow is greater, sorry, the Reynolds number is greater than about 2000, more or less, it's approximate. There are many situations that could come into play, like environmental situations and so on. Then the flow is more likely to be turbulent. So there's always this critical value. Of Reynolds number below which flows are laminar and above which flows are turbulent. The exact value depends on the flow situation. So a laminar flow, as you say, increase the velocity, for example, could experience an instability and become turbulent. And this is what we'll see in pipe flow as you increase the velocity. But let's see, but you see Reynolds number has several parameters in it. And therefore, we can increase the velocity or perhaps make things bigger, and it would also increase the Reynolds number, right? Or change the viscosity. So let's look at, in this case up here, in this movie, the Reynolds number is different because the viscosity of the fluid that is being poured is different. So let's look at other examples. Here, what we have is, in the yellow case, we have a low viscosity fluid, the yellow one here. This is low viscosity. And we have a little small ink layer that's been poured on top. And the container is going to start rotating. So, oh, that one's first. I got my things wrong. Let's try that one. Okay, look at the yellow one, okay? The yellow one first. That's low viscosity fluid, and as the container starts to rotate, only the layer which is closest to the container gets sort of pulled with the container, and the layer of fluid in the middle is really not moving. You see? The reason is that there's inertia effects dominating. The fluid in the middle doesn't really want to move very much. It's inertia. It's just you know, dominating the whole situation. And even though we're rotating the container, not much is happening in the middle. It takes a long time. There's a lag between the container starting to move and the fluid following, because inertia effects dominate. In the orange fluid, what we have is that the fluid the container starts moving, and almost immediately, for some reason I can't start it again unless I do this. Almost immediately the fluid follows. The viscosity effects are so large that inertia is not an issue here. The fluid follows the container immediately. So on the right, the fluid is dominated by viscous effects. On the yellow case here, the fluid is dominated by inertia. Yes?
So in the previous slide, you can go back to it.
This one?
Yeah. So it's just the dye that's going on?
It's a dyed fluid of different viscosities. This one is very, very, very viscous. This one's a little less. This one is a little less. And the final one is very low viscosity.